Okay, so let's continue with our theory of open quantum systems. So just a reminder, we've looked at the now generic case. Okay, we have a small system, couple of weak so large path, and this interaction is some sense weak. I mean, if it's completely arbitrary, of course, we cannot do anything. But actually, this describes a situation which is often the case. One example would be an atom with well-defined level structure. We can drive Rabi oscillations, but it's coupled weakly to a set of electromagnetic vacuum modes. And this, as we know, kind of then leads to an irreversible decay of this atomic state. And this type of physics, okay, we now thought about, okay, how can we systematically describe such systems? And to do so, okay, we started to derive a master equation for this system. Okay, so let's start from the beginning. So we have this separation, system Hamiltonian, path Hamiltonian, and some interaction. The path, what we usually talk about, will be kind of some set of bosonic oscillators, harmonic oscillators. The path, in some sense, that we showed with this small toy example. I mean, if we couple to one mode, we get essentially Rabi oscillation. Okay, if we couple to three modes, also the system will be complicated. But if we couple to many modes, and especially a dense set of modes, okay, we saw that then there was this exponential decay arising from this theory of this Wigner-Weisskopf theory, which is a simplified version. Okay, so you want to have been a similar system, and then we have something like interaction. So we create a excitation in the path, and then there's this operator C, which at this stage we leave arbitrary. But this is the interaction. So whenever we create an excitation in the path, what happens to the system? Okay, C is a system operator. This could be a sigma minus. We create excitation in the path and the atom goes down. But it could also be a different operator. Okay, you could also have a path where you would excite something in the system. Okay. Yeah. Okay, so this is the general setting. And just a reminder, what we did now is we assumed, okay, on the whole system dynamics, I mean, Schrödinger's equation must be valid. Okay, so we start with Schrödinger equation. When you convert this to a density operator, it looks like this commutator here. So von Neumann equation, but this is essentially a Schrödinger evolution. And one thing that we did right away, we transformed away all the fast energy scales, okay, all the absolute energies of the photons of the system, so that so we moved the interaction picture such that only the interaction is left. Okay, this is now Hamiltonian, can be time dependent, but in some sense this is weak. Okay, so we can do perturbation theory in H int. Okay, so what we did with this equation then, we simply started to integrate it. Okay, we integrate both sides, so then we go rho of S is rho of S of 0, and then minus I over H bar 0 to T, and then whatever is on this side. Okay, integrated as a kernel. And then we can take the solution and insert it back into this equation, and then with this we get in principle a hierarchy that has this form, so first you have a single integral with H int at T1, then we get a double integral, and so on. And in principle, we can continue this hierarchy. Or what we did, we stopped after the second approximation, second step. Okay. So and again, this equation is still exact, but it doesn't help us a lot because rho of S of t is given by rho. Okay, should actually be S here. Rho. No. Okay. So another point what we did, okay, we integrated this equation, then we also traced out the path degrees of freedom, because that's what we wanted to have. Okay, we're not interested in the full density operator, but only on the subsystem. Okay, so we traced over the path, and therefore we get the resistant density operator. And here, okay, there's still path operator, system operator. So here we still have this trace left. Okay, but you see that somehow the density operator at time t still depends on the density operator at t2. Okay, so if we don't know anything more, this doesn't help us anything, because the solution depends on the solution itself. Okay, this is just a formal way to write everything. Okay, but then we started to put in approximations, and the first thing was roughly given by the Sporn approximation, weak coupling approximation, and this is first of all has to do that here in this density operator, I mean system and path are coupled, but we assume the path has many degrees of freedom, is very huge. So if you put one excitation in the path, it's essentially ineffective because it's distributed over all these modes. So if you look at a single mode, it's hardly effective. So what we assume now in this type of form is that at any time, the full density operator can be written as the system density operator times the stationary path operator. Okay, so usually this will be either all the modes in a vacuum state or all the modes in a thermal state. Principle can also be more complicated, but we assume, okay, somehow a stationary object, all the modes are independent of time, they're in equilibrium, but the system operator can change. Okay, so the effect of the system on the path will be neglected here. And then based on this factorization of the density operator, okay, we can then also say that if we now look at the first term and we trace over the path, and remember in the Hamiltonian, we have something like on the path side, we have an operator like B or B dagger. Okay, so if we trace this guy, I mean, it's commutator, but for each of the term, we get the same thing. You take the trace, and what actually happens here is that then this expectation value will be proportional to the average of the B operator. Okay, and if we are in a vacuum state and this B is bosonic mode, so in a thermal state, then there's no average field in the system, and this will be 0. Okay, so we can set this first order 0. And then at the last, I think at the end of the lecture, we also mentioned that, okay, even if this would not be 0, we could, take essentially this expectation value and redefine this part of the interaction into the system Hamiltonian and get a new effective coupling to the path, which is now where this vanishes by construction. Okay, so you couple something which has a mean value, you take the mean value and put it into the system Hamiltonian, and then what you're left with in the path interaction, you couple to an operator that has no mean. Okay, so if you go back to this last slide, just remind you, but most of the time this is anyway the case. Okay, let's assume it, and then this guy vanishes. Okay, so this is gone, and now what we can do, we have the rho s of t is proportional then to this double integral. And now what we do once this first order term is gone, we take again the derivative of this guy here. Okay, so we have traced over the path degrees of freedom, we eliminate the first order term, and then we take the derivative. So what happens? Rho dot, this is gone, equals, and from this term, if we take the derivative, okay, we just replace if we get rid of this integral, and instead of t1, we have t. Okay, so let's do this. So we integrate it twice, we remove the first order term, and then we take again the derivative. Okay, and what we then have is now an equation, rho dot at a given time t, right? Depends on the integral 0 to t, t1. And now what you see here, the second order term is this double commutator with this h int, this interaction Hamiltonian evaluated at time t and t1. And here we still have this density operator of the system. Okay, so you see the derivative of the system operator depends on the system operator at all previous times. Okay, this is again this type of problem that we have an equation which is now non-local in time. Okay, but now we can actually go back to our Wigner-Weisskopf theory. Now there we had the same problem, but instead of having density operators and commutators on, we had a little bit simpler expressions. But we also had something that depended on some t minus t1, okay, some time difference here. And this function back then, this was very sharp, okay? It was almost a delta function, and this allowed us then to get rid of this integral and make a time non-local equation, okay? So we're now trying to do the same, look around the same spirit, okay? So everything we do is under the same type of spirit, but okay, the mathematical objects that we have here look now a little bit different. Okay, but actually what we want, okay, so again, this is this called of Markov approximation, so somehow we must make use of the fact that we emit into the path, and this excitation distributes very, very quickly, then it dissipates, it goes away. Okay, and to see how this now arises, okay, so I mean, think about it. So what do we have here? Okay, so there are now these double commutators, okay, but think about one of these terms, okay, then it's h int, and rho, and we take the trace over the path. Each of these interaction Hamiltonians has a B or a B dagger, okay, so if you would, then we have let's say a B dagger, a B, and on the path side, they are acting on this rho, on this path, and then we take the trace. So what we have here, what we'll end up with is something that looks like a B. Let's call this term. B is P1. So we have expectation value of these operators. Okay, we have two of these operators, the all type of different combinations. But then we take the trace over path, average over this path density operator, so we get expectation values of this form. So let's now evaluate such type of expectation values, and just to keep in mind. Okay, so this is again our definition of the B operator. It's centered around a certain frequency, omega 0, and has a certain bandwidth that we call here now delta. Okay, so this is the bandwidth around this frequency. And again, in this continuum notation, these B operators, they fulfill this commutation relations, which are now delta correlated. Okay, because instead of having discrete sums, we're already working here with integrals. But you could do the same thing with just replacing this by discrete sum. Okay, and now what do we get? Okay, so let's evaluate such a expectation value. We plug this in. This is our definition. We get now two integrals, the omega prime. They go above the same interval. Then we have this trace, this expectation value, is trace times the, and then we get this operator in between, and then we evaluate it with this equilibrium density operator. Okay, and now we put in, so here we have a dagger, so that's why we have a B dagger, e to the plus I omega t, T1. Okay, so here we have T2 times T1 and T2. And the other one is a sum of these omega prime operators, and they are B, so they oscillate with minus I omega prime T2. Okay, so, and now, okay, what is this expectation value? So think about this row B, so this row B can be maybe a vacuum state. So you see if it's a vacuum state, this type of expectation value would actually give you 0, okay, because B acts in a vacuum state. But another possibility is that this is a thermal equilibrium state. Okay, what does it mean? In thermal equilibrium, all the modes, okay, if you think about statistical physics, you have a bunch of harmonic oscillators in thermal equilibrium. Each of these modes is separately in this thermal equilibrium state. So that's we'll write down thermal equilibrium, so there'll be some partition function. And then in principle you have, if you write it in terms of these discrete modes, so the sum over n h bar omega n a n dagger. That's the way it is. P n. Okay, so the main point is that this system operator will be diagonal. Okay, so if you have destroy one mode, one photon at frequency omega prime, and they create another one at omega, then this expectation value will give you 0. Okay, because you have a mode density operator that is diagonal. So the only point where this can make a non-zero contribution is if if omega prime and omega are the same. So you get here then something that's proportional here to a delta function, and the expectation value is given by the thermal equilibrium number. And if you're, you must be careful here. Okay, T omega and omega prime will be the same, but what's left here is I omega T1 minus T2. Okay, so if this is maybe with this continuum approximation, so what you would have if you write down a sum, it would be the expectation value of a Bn dagger Bm and rho 0 trace rho 0. So if you put in here a diagonal density operator, if you remove one photon from one mode and add it to the other mode, this expectation value gives 0. Okay, and the only thing is, so then this guy in a discrete language would be just delta n m times expectation value of Tn in the equilibrium occupation number. Okay. So this is essentially what's written here. Okay. Where now what is this n thermals? Just remind you, a single mode in the thermal equilibrium state has a mean occupation number that is given by this Bose-Einstein statistic. Okay. So 1 over e to the h bar omega over kBt minus 1. Okay, so in this, of course, this occupation number depends, is in general frequency dependent. Okay, if you have low frequency, then this occupation number is higher than in a high frequency. And now putting everything together, but let's say the main point here is we sum over all these frequencies, and the only contribution where this expectation value can be non-zero is when you evaluate this expectation value here for the same frequency. Okay, so that's why I have this omega, this delta function here, and then this simply eliminates one of these integrals. So let's put it in. Okay, so then we get this correlation function that we get here is then still an integral of this frequency band. There's this energy scale still in here, and there is this frequency dependent n thermal. But now, okay, so now we make our usual assumption. We have a path, or let's say a central frequency that is very high, and then we look at small variations around. Now this bandwidth delta is still small compared to omega 0. So therefore, when I put this thermal equilibrium number, if I put omega 0 minus delta or omega 0 plus delta or omega 0, doesn't really matter. Okay, think about again this optical case. Omega 0 is 10 to the 15, and this bandwidth can be 10 to the 12. So there's still essentially all the same frequency. Okay, so this is like we assumed that a coupling constant doesn't vary a lot with the frequency. We can assume here that the thermal occupation number is approximately the same and essentially equal to n thermal of omega 0. Okay, so then we can put this in. We take out the overall frequency scale. That's still a fast oscillating term. And then what you get is simply an integral from minus delta to delta over this exponential. This gives me this effective delta function as a function of T1 minus T2. Okay, so this would be a typical, coming back to this equation. So we have this whole term. If we start evaluating all these terms, there will be contributions such as B dagger, now, okay, here the time is, so I choose just point T1, T2. Here then can put in T and T1, but there are two time correlation function of these operators. And because they are broad bandwidth and let's say they are kind of delta correlated, so therefore one of these integrals cancels out through this delta function. And what we have is then something that is delta correlated in time and is proportional, in this case, to the thermal equilibrium number at the characteristic frequency. Okay, and the same thing you can do, of course, also for other combinations. So if we would now revert B and B dagger, because everything stays the same, except that in this type of accumulation values, you would have now a B n dagger, Bn dagger. And now, okay, so this, even when it's acting on a vacuum state, it creates me an excitation. So therefore, that's why this is proportional n to delta is diagonal and proportional to n thermal plus 1. Okay, so this contribution also is finite if we are in a vacuum state. And then you can also have combinations where you have a B, two Bs, or two B daggers. And here, I mean, even though you could think about different classes of reservoirs, in general, if you think about vacuum or thermal states, then such expectation values are 0, okay? Because these are, you create what is the expectation values of 2 photons. So this would be something that is, if you think back to a discussion about squeeze states, you can think about squeezed reservoirs where this could be finite, but in general, thermal states and vacuum states that we're dealing with right now, these can be set to 0. Okay, because simply everything is symmetric.
Is this true also when T2 and T1 are the same?
Yeah, so because this would be, so you think about again a finite discrete set of modes, and if you have now something like 2 B's and you so either act on this in the vacuum state, or if this is a thermal state, then this expectation would be 0 because this would be would have a preferred direction. I don't know how these different ways to see it, but let's say the average of in a thermal, if you have a thermal density operator, then the average of a B squared is 0. Yeah. Okay. So this is essentially the thing that we need. Okay. So we want something. So what we have recovered here is again this delta function. So something which is very localized in time. I mean, it's not an infinitely sharp delta function, but the sharpness here comes from 1 over this bandwidth. Okay. So if I evolve slowly compared to 1 over this bandwidth, then this function here, that's the sinc function that we defined also previously, is essentially a delta function. Okay, so and also, I mean, if you think about this type of what is this correlation function? So you have, so this expectation value. It's essentially okay. You have you're in the equilibrium state. You create an excitation at point T2, and then you destroy another excitation at a later time, for example, T1. So this is, so these correlation functions measure, think about the atom, you put a photon there, so the atom is here, and you put a photon at this point at time T2. And then you see at a later time, is the photon still there? Okay, and of course, if you have a 3D and the photon is fast, okay, we simply disperse. So after a very short time, the photon will not be there, and that's why this correlation function also decays. If you would evaluate this for a cavity, a single mode cavity, you put an atom, puts a photon in the cavity mode, and if it doesn't decay somewhere, then somewhere else, then it just stays there. Okay, and then this correlation function would actually show oscillations, long-time oscillations. Yeah, and this, and what I principle started, okay, this consists, I mean, this is of course a general now evaluation of these correlation functions, and the reason, motivated in the beginning, why do we actually evaluate these things? Because we need them now to evaluate these time they naturally appear if we calculate now this trace of this double commutator. Okay, so let's put these things together, what we know so far. Okay, so and this now, okay, we haven't evaluated this full double commutator because it's a little bit messy, but what we now know, let's go back. Okay, so we have in this whole expression, there will always be these correlation functions popping up, and these correlation functions will essentially be have a delta function t minus t1. Okay, so at least a very sharp function. So this means that in this whole integral, the only thing that is relevant is then again the point, so that the integral evaluated essentially at the upper boundary here. Okay, so independent of how these expressions now look in detail, we know from this integral we essentially only need the system operator at the upper boundary, and we now do. Again, this is now called this Markov approximation. So we replace now this So this is then the Markov approximation. So what we now did in this last step, we replaced in this whole integral, we replaced this rho s of t1, we replaced by rho s of t. Okay, so rho s d dot, the time derivative, is now proportional to the system density operator. And the other small thing we did is you remember previously we had the integral from 0 to t, and we now replace this by minus infinity. You see that, if this function here decays very quickly, then it doesn't matter whether we integrate from 0 or from even further, because it's anyway doesn't contribute to the integral. Okay, this is just now to make everything slightly easier to evaluate. Yep.
Why can't we, like, if all of the contributions have the delta function in t, why can't we get rid of the, like, why can't we substitute the h int?
Yeah, so now it depends a little bit now in a bit more detail. So I mean, yeah, so there's something, okay, this is a delta function, okay, but this might not be, so it's a delta function on the evolution timescale of my system dynamics, okay? But it could still be the full temporal form of this function can still be slightly more complicated. Okay, so I mean, for this specific example that I just showed you, you could in principle make this approximation. Maybe let's go through and then maybe come back to this point.
And for the first h int, that t is correct.
That t is correct, yeah. So this is let's go back to the
Yeah, right. Okay,
yeah, so we started from this t1, t2, and then we took the derivative.
Yeah.
Yeah.
Sorry.
And then this is yeah. So maybe again, the thing is, so we used, so here we specifically used a very simple type of model. So it could be maybe a bit more complicated, this integral. There might be density of substates and so on. But the thing is that the only thing that we want to use is now that these correlation functions of these path operators, they have something which is now fast decaying on the scale of the system dynamics. Okay, that's the only thing we make, and therefore we can, in this whole integral, we replace the system density operator at t1 with the system operator at the upper boundary. And yeah, this makes now a system local in time. Yeah, it's just mentioned, okay, we can set then everything, because anyway, anything just depends on the upper boundaries. We can set the other one to minus infinity. Yeah, the path, okay, quickly forgets, so it doesn't really matter when it started. And then just a reminder, I mean, everything, it looks a little bit more nasty, more complicated objects here, a lot of operators and tildes and times and so on. But essentially what we do is exactly the same as this Markov or this approximation we did with the Wigner-Weisskopf. Okay, so we have something, and again, this must not be an exact sinc function. It could also be for other paths. It could be something like a Gaussian or something more complicated. But it should have, a support primarily at this point time t. And the system state, evolves slowly on this scale 1 over delta. And this is, again, like in the previous calculation, at this stage, we haven't shown that this is the case, but this we can then check once we derive our equation. We can go back and check that everything is self-consistent. Okay, so this is our approximation. So now, of course, what we still need to do is to evaluate this object. Okay, so what do we get here? And yeah, so evaluation of the remaining integral. And this looks, look at this, first look at it, there's all these double commutators and a lot of terms actually in there. We can, always make it a little bit more systematically, but let's, in principle, we have a double commutator. We started with this double commutator. Okay, so this gives me 4 terms. If I multiply out this double commutator, but they all have a similar structure. Okay, so let's take one of them. And here I took the first term, okay, so where I have h int at t, h int at t1, acting on rho system at point t and rho path in the equilibrium state. Okay, so I need to evaluate now this term. And let's go back to our definition of h int. Okay, so we what do we have? H bar squared of gamma. So I use this convention here. And then we have a C of t, B dagger of t plus C dagger of t, D. Okay, and so again, this interaction Hamiltonian has two terms, so h squared in principle we get 4 terms, but then you remember that 2 of these contributions you will end up with B dagger or BB, okay, and they vanish. So the only combination that we can get out of them is a B and a B dagger and a B dagger B. So now remember that here we take the trace, but only over the path degrees of freedom. Okay, so and this in particular, you have to now be a little bit careful with operator ordering. Okay, so we trace over the path, so we can commute all path operators. We can in principle commute, but do permutations under the trace. Okay, we cyclic permutations. But for the system operators, this is not the case. Okay, so here we start h int acting from the left, another h int acting from the left in rho system. So therefore, we also have these operators like that. We are not allowed to make change the order here. In the path, okay, I mean it's also in this case it's the same ordering, but in principle we could also now move these operators to the other side and so on. Okay, so now we still have these type of integrals here. And now we need to be a bit careful with all the assumptions that we made. And in particular, if you remember that this rho tilde is the evolution in the interaction picture. So what we have here is actually the C of t. So remember that this operator here that we have, C of t, is e to the I system Hamiltonian t c to the minus I system Hamiltonian t, or maybe another equation. Okay, so this is a time evolving operator. Okay, so in principle, this can also be complicated object here. But the only thing that let's say that the thing that we now want to make, so we know all slow time scales. Okay, suppose I have now a 2-level system. I drive with the Rabi frequency, the atom decays. I drive with the Rabi frequency of a small detuning. These are all slow time scales. Okay, so these I can neglect in this time evolution. But there's also the fast time scale, and think about this as the C for concreteness. Think about this being sigma minus operator, then this transformation and the H system is H bar omega EG EE, and that is my atom, and this whole operator here will be sigma minus e to the minus I omega EG times t. Okay, so I must be careful when evaluating now these integrals. I have some parts. This is evolution in the interaction picture. This is very slow. I have in the evolution of this operator, in principle, also the system Hamiltonian. You know, I can have a Rabi frequency included in the system Hamiltonian. But this is very slow. Okay, 1 megahertz, let's say. So I can forget about it, on these time scales. The tuning, 10 megahertz, I can forget about it on these fast time scales. But there is also in our definition, we also have included the bare evolution with the characteristic system timescale, okay, with the atomic transition frequency. And this oscillation is fast compared to these expectation values and so on. Okay, so therefore I also cannot directly make now, if I do a delta function approximation up there, I will not capture this evolution timescale here. So therefore, what I now do is I say my jump operator, okay, and this depends now a bit on the system, but for our basic assumptions, we have sigma minus operator, or we have an annihilation operator. If we talk about harmonic mode, it will actually, this evolution, you will have this type of evolution, okay? So the operator at point t is the operator at t minus tau times this evolution time, this oscillating phase factor. Okay, so I can convert one of them, so have these operators acting on the system at the same time, and this additional phase factor I keep track of, and this gives me additional oscillating phase with tau. So why is this? So what do we then get? Okay, so let's do this. Okay, so all the evolution of these operators is now included in my e to the I omega s tau, the difference between them. And then this is essentially time independent of my scale. Everything is just evaluated at t. And the only integral that I get here is of this type. And of course, the reverse term. Okay, so I have a b dagger b here and a b dagger b over here. And you have to keep track of all the phase factors correctly, and then you get a plus in here, minus. Okay, and now we so why did we do all these things? And maybe just to keep track of. So also in this correlation functions of the p operators, we had this delta function, but we also, if you're accurate, we put out a common frequency in front. Okay, and this type of frequency, and here I see I've changed notation a bit, so it should actually be would actually correspond to this system frequency. Okay, so because I couple. I have my system frequency, and then I have a bandwidth around this frequency. So this will now, if you see this phase factor, that combines with the phase factor I got from this commutator, and therefore this then drops out. Or maybe to be a bit even more general. So what you get here is now, okay, this trace, this correlation function is just so this correlation function is essentially the expectation value. Just pointed out. Okay, so one thing that we can now assume. Okay, you see you have a correlation function b of t, b dagger t minus tau, acting on the equilibrium state. Okay, so everything is here time dependent. So this means we generate an excitation at t minus tau and then destroy an excitation at point t. And this process, because we started in equilibrium, cannot depend on time. So, I mean, this is a property. If this equilibrium density operator, then we know that these correlation functions are independent of the absolute offset in time, but just depend on the time difference. Okay, so I can always shift these correlation functions, both of them by t, and again by shift them by tau, and then by t, and therefore I end up, it's only the time difference that matters, and that's why here this correlation function corresponds to b of tau, b dagger of 0, and then multiplied here by this frequency e to the I omega t. Okay, so to summarize once more, is if we look at this first term, I get the effect on the system operator is c dagger c acting on rho from the left. Okay, and everything else here is now an integral, and this integral I write here as I minus is nothing else but this correlation function and taking the Laplace transform of this or the Fourier transform of this correlation function at the frequency, at the system frequency omega s. Yeah.
Could you repeat why there's the space factor like in the next to bar, like why is it coming from the system omega?
Yeah, okay, so this is now, let's go back here and see what we're doing. So what we start out with is, or explained here, is this form. Okay, so we integrate over this variable tau. Now we have the system operator t and the system operator t minus tau. And these again for here this density operator here is in the action picture. This evolves slowly, but these operators, and now if you think about a sigma minus operator, then the sigma minus of t will actually oscillate with the intrinsic system frequency. So for example, omega EG. So this is a fast oscillation. So if I would neglect this, then I make a mistake here. Okay, so I cannot, my delta function that I've done before, is a delta function on a much longer time scale. Okay, so I have to keep this basic evolution. So if there's a fast dynamics here in the C operators, I have to explicitly include it. And therefore, if we then go to the final result, so what actually we do is we evaluate this correlation function of these path operators now at the system frequency. Okay, so that's so if you think about as say just a single harmonic mode at tau and a theta at 0, and just think about a vacuum expectation value of this term. Okay, so then this correlation function will actually oscillate e to the minus I omega. Let's call this, so this is a path operator, so omega bar times t times tau, and in this case times 1. Okay, so this correlation, the path operators, they create excitation think about it. Okay, so the path operators, they live at the frequency omega 0. Okay, so they have a high frequency and some smaller frequency around it. Okay, so if you calculate correlation functions, what happens if I create destroy an excitation and then I create it later, or the other way around? Then these expectation values will oscillate with this fast frequency. And at the same time, also my system operators in this interaction picture, they also oscillate at a fast frequency. Okay, so this is the omega EG, the atomic transition frequency. This other omega 0 that I had before, that's kind of the typical frequency in the photonic path. Okay, so I have to therefore keep track of this frequency and in this frequency, and what happens is essentially that the system frequency will be approximately the same. So multiplied on this by omega s tau, and therefore both frequencies are the same, are big, but they kind of cancel each other out approximately. So yeah, so we have let's also go back to the usual the simple example we had. So we have this G E, and then we have kind of the bath modes, the photonic modes around this frequency. Okay, so here's omega 0. This is my system frequency. And what I get, what this essentially says is I want to look at this correlation function in the bath, but around this frequency that is given by the typical system frequency. If I would neglect this, I would actually evaluate the bath correlation function close to 0 frequency. Okay, I would couple to these modes here. So, I mean, everything, so if you have, if you do it very naively, okay, you would say you probably forget about this factor, you probably forget about this phase factor, and you would also get it correct. But if you write now down this formula and forget about this oscillation factor here, you evaluate this correlation function at 0 frequency, but your path has, the relevant frequency is actually given by the system. The system emits an excitation that has exactly this frequency here. So we want the correlation function at this frequency that enters into our dynamics. Okay. Yeah, maybe just let me summarize and then maybe go back to some of the details. Okay, so this would be now one. So you see one of these terms, one of these double accommodated terms will give me now these contributions. Okay, a C dagger C acting on rho with this correlation function B and B dagger. And you see that this correlation function is also there if you're in a vacuum state. And there is kind of an opposite term here, C dagger, that has this correlation function which would vanish if I'm in a vacuum state, but if I'm in a thermal state, then this is also there. Okay, so I have these two contributions. One of them is there even if I'm in a vacuum. This means I can always emit an excitation. Okay, so this term, this corresponds to emitting into the vacuum. But if I have thermal excitation, I can also absorb energy from the environment. Okay, so if an atom and a lot of photons, you can have the atom in the ground state and absorb energy from the environment. But this is only possible if this correlation function is non-vanishing. So yeah, and now, okay, this was now one term, and now you can go through all these different terms. You summarize all these integrals. Essentially, you will always get roughly the same type of effects or steps that you have to do. And each time you will counter slightly different correlation functions. So here you just have to make use of, for example, we can shift everything by the same point in time. That's just this stationarity. And if you think about how these correlation functions, these time-dependent operators are defined, you see that something like this, if you are at minus tau here, if you change the time, it corresponds to actually just a complex conjugate of this. Okay, so each of the contributions gives you a slightly different result. But if you then sit down and put everything together, you actually end up now in the following equation. Okay, so this is now everything put together. So this rho S, I'm also transforming afterwards back into the Schrödinger picture. So therefore I have the full system Hamiltonian here back again. And I essentially get something that is Hamiltonian contribution, okay, system evolution. There's a small additional Hamiltonian part. And then I get these other two terms, okay, which are not, I cannot write in this just simple commutator. And you see, this is one of the terms that we had before, C dagger C from rho and the C dagger from rho. Of course, if you act with this induction Hamiltonian from the other side, you will also expect that there's something like C dagger C and C dagger. And there's also a combination if you work out this commutator, H, you apply H from this side and H also from the other side, and therefore you also get these two contributions here. Okay, and this is a rho dot. So what you have here are rates. Okay, so a rate A minus and a rate A plus. And these rates are now given, okay, quite generically, the real part of these integrals that we have obtained before. Okay, so also now more generally, so we have, so suppose you have, you know, the system path interaction, you have a path operator. It can be much more complicated than the situation we just described. What you do, you evaluate these correlation functions, you do a Fourier transform at the system frequency, and with this, then you get from this evaluating this integral, you get a rate, or taking the real part, you get a rate, and this will appear here in this master equation. Okay, and so again, this a plus a minus, they will be proportional to the real part, and that's why, you know, we have to be a little bit careful with this complex conjugates and then taking the correlation functions correctly. But then you will also get an imaginary part, and the imaginary part of this integral will actually contribute to this Hamiltonian. And if in our case you write it out like this, you have to evaluate the imaginary part, C dagger C, and the imaginary from the other C dagger. Okay, so this is the general type of results that you get. Okay, so and that's why also coming back. I mean, if you now have a little bit more complicated environment, and that's why we didn't do the delta function approximation right away, because we have to keep track of this detail dependence, and now we can put in your, you know, arbitrary P operator. You can put, for example, the electric field operator that had been before for an atom, and evaluate this full time integral to the Fourier transform, and then get these rates and also these Hamiltonian corrections. Okay, but this is actually the essential point. We have now derived an equation for the system density operator, and let's say apart from some small Hamiltonian corrections, we get the evolution now doesn't look like a commutator anymore, like a Schrödinger equation, but it has this more complicated form. And just keep this in mind, you know, for the rest of the lecture. It's always of the type 2 jump operator 2c rho c dagger minus c dagger c rho minus rho c dagger c. Okay, so this would be kind of the term that describes emission into the path, and then the reverse, so just replace c and c dagger, corresponds to energy absorbed from the path. But it's always kind of this structure, so keep this in mind. Okay, so let's maybe summarize what we have obtained here. Okay, so just a small remark on this H prime. So we see that any coupling, this so far we didn't pay attention or didn't get from the Wigner-Weisskopf theory. We have Hamiltonian correction. So whenever you couple to the environment, think about this, that you can emit the photon and it escapes, but you also can virtually excite, let's say, a high frequency photon and then come back. So this will give me a second order shift. Okay. And this, in general, both contributions appear at the same time. If a broad path, you can couple the modes, resonant modes that then travel away, but you can also couple the all off-resonant modes, and they will give you a frequency shift. And this is what's essentially written here. And this frequency shift can also be, so if you go back to the atom coupled electromagnetic field, it can be interpreted or associated with the Lamb shift. So you have probably heard about this. You have an atom coupled to a quantized electromagnetic field. It will actually have a frequency shift. So there's this Lamb shift, famous Lamb shift, that essentially comes from this type of coherent interaction. So there you don't emit the photon, but just whenever you couple one quantum system to another one, you expect frequency shifts. Okay, that's naturally occurring. I mean, usually we don't care too much about this. There can be a situation where it is important. In the following, I will not care too much about it, because if you, for example, think about an atom, it is never decoupled from the environment. Okay, so whenever you measure the frequency of the atom, it already includes this term. because you always measure, you probe with the laser, you probe the atom that's coupled to the electromagnetic field. Okay, so very often you cannot just, you don't know the bare Hamiltonian because it's always coupled to the environment, and therefore these corrections often included already in your system Hamiltonian. Okay, so in the following, I will also assume that this is the case. There are certainly also exceptions where this correction here becomes important. Okay, so having now obtained these results, okay, so first of all, you can worry about, did we do all the calculations correctly? And also, does this equation make sense at all? And one good way, and that's also, you know, at some stage you have to write down this master equation, for example, for the exam, write it down. And then half of you will kind of mix up the order of these C's and C daggers, which is natural because you haven't worked a lot with it. So how do you check that you get it correctly? Okay, so a first check is that this gives a valid equation for a density operator. And one thing that a density operator has to obey, it has to conserve the norm. Okay, it has to be normalized to 1 for all times. So in other ways, the trace, so if the trace always is 1, the trace of rho dot must be 0. Okay, so the minimal requirement, I mean, it doesn't tell us that's really the correct equation, but at least the trace of this, if I take the trace on this side, it must be 0. Okay, so now how can I see this? So remember, if I now take the trace over the system degrees of freedom, I can actually have cyclic permutations between all the operators. So what I do is now take from these two C rho C dagger, I take one of them, and I have so C rho C dagger under the trace. So this now is trace of the system is of course equal to trace of the system. I can put it to the other side. Okay, and then one of them terms just cancels this equation, this term, and the other one, I bring the C on this side and I also cancel this part. Okay, and of course the same, because C and C dagger are just reversed, applies for the second term. Okay, so it's always a good check whether you messed up something in writing this down. Okay, and it also, okay, we did a lot of approximation, but at least it was not completely wrong what we got. So it's still something that preserves probabilities. Then another, okay, next remark I want to make is that, okay, we did now everything for an atom coupled to one path, or let's say a system coupled to one path. I mean, in general, you can see that, okay, you can have coupled to the electromagnetic environment, you can couple to phonons, you can have decay, you can have dephasing. So everything we did so far, I mean, can be readily generalized to this type of master equation, which means we have rho dot, and okay, here I remove now the subindex S, is commutated with Hamiltonian, and then some sum of this type. Okay, so for each of these CK now reflects a different type of coupling to the path, and gamma k would then be the corresponding rate that is associated with this. Okay, and the thing is now not that you the statement that's, I don't have a citation here, but that's why it's also called Lindblad form. What Lindblad showed is that this is actually also the only possible form that you can have. So what you want is a local equation for a density operator, and the density operator has to preserve the trace, and it has to preserve positivity. Okay, so that's slightly different. If you have trace and one entry is 1, the other is -1, this would still be 0 trace. But it would not correspond to probabilities. Okay, so you have to make sure that all the eigenvalues, so positive, rho must be positive, all the eigenvalues must be positive, they must correspond to probabilities. So there's a slightly stronger constraint that the equation you can write down must preserve the trace and the positivity of the density operator. And then you can show mathematically, it can always be written eventually in this form. Okay, so it's often not immediate to see. So sometimes you have here quite complicated jump operators. They involve, if you have many atoms coupled to the same environment, you can have sums of sigma minus and sigma plus operators. So it can be complicated, but the statement is, if it's a trace preserving and positive map, then it can eventually always be, if you rearrange it, written in this form. Okay, and you also see in this type of form, you can also interpret now, before we took this, we coupled to a thermal reservoir where there was this minus term and the plus term, and you can simply associate, okay, two terms, two different rates, A minus and A plus, and two different jump operators. One is the jump operator C, in the other case, it's C dagger. Okay, so it's right away included in this definition. So then something that might not be, or you have to realize when you look at this equation, because it's a little bit a new type of form with all these operators acting from left and right and this density operator. But keep in mind that this is something where we have rho on this side and rho on the other, so rho dot on the one side and rho on the other side. Okay, so this is a linear equation. So if I multiply here rho with a factor of 2 or add rho 1 plus rho 2, this equation is linear. Okay, so even though it looks now maybe a little bit strange and complex, I can write it in the form, okay, it's a linear equation. So this is rho dot is some linear operator acting on rho. Okay, so if I have a linear equation, okay, I can, it might now, linear equation usually mean matrix acting on a vector. Okay, so now our rho itself is a matrix, is an operator, but still, it's a linear equation, so I can express my rho into an extended basis. Okay, so I can every matrix, I can also just take the elements and put them in a vector form. And then I've represented my density operator in a basis as a vector. And then this L, this complicated operator, would just be a bigger matrix. Okay, so every any linear equation you can write down, if you just write it in a certain basis, you can write it as a vector dot matrix times rho. Okay, so because it's now this L that I define like here, it's then called Liouville operator, and because it's an operator acting on the space of operators, it's therefore called a super operator. But in principle, everything we do here is matrix times vector multiplication. And if we have such an equation, rho dot is L rho, we also know the formal solution. Okay, it's simply the exponent of L times T acting on the initial state. Okay, so we can write down formally, this is my evolution, like we do, we integrate the Schrödinger equation. Schrödinger equation, here we have an H and we have a minus I, and therefore e to the minus I HT, and here we don't have the I, so therefore it's just e to the LT. Okay, so that's just the formal solution. It's a linear equation, and in principle, we can especially see this when you do numerics, we can represent this density operator rho. We can represent as a vector if we choose the right basis, and then this L would be a matrix, and then here we just have a matrix exponent to calculate the solution. Okay, so we can, we have this master equation. We can solve it, of course, not always exactly and analytically. What else can we, so very often, okay, so this gives me immediately the density operator at a later time. But a lot of time we don't want the density operator, actually we want to calculate expectation values. That's the thing that we are interested in. So how do I calculate expectation values? Okay, so keep in mind, if I write something like this, expectation value of O at a certain time is nothing else but the trace operator, so O is an operator observable times rho of T. Okay, so now let me see how does this expectation value evolve in time. Okay, so let's simply take the time derivative here, O dot, then I have an equation of motion for the observable, and on this side I just put the time derivative of rho, so rho dot here. Okay, so if I calculate time derivative of this observable, it's just like that. But now for rho dot, I have this expression, okay, and especially have this expression from before. So can immediately put this in, okay, so instead of taking here this rho dot, I just put in this master equation, okay, commutator with h rho and these terms, okay, and whatever, so this is the master equation, and then before taking the trace, I have to multiply everything with this operator. Okay, so this would be now the equation of motion for this operator O. And now what you can see is that here, now I have this commutator, so I have a few terms, but everything is under the trace. Okay, so under the trace, I can do cyclic permutations, and I can reorder this whole expression a little bit. So I can have here OH, let's do a few. So what is O? H rho. Okay, under the trace, I can write this as a trace. The first term is O H and rho. And the second term is trace O rho H. But under the trace, I can put the H on the other side. And all together, I get now a trace. So you see OH minus HO, so commutator OH and multiplied by rho. And that's nothing else than the expectation value of OH. Okay, and the same term we can do also over here. Reorder them, so always bring the rho to the right. And if I do this, cyclic permutations, I end up now an equation for the expectation values. Okay, so I've now essentially gotten rid of the density operator itself, but this is now an equation for the expectation values. And you see, okay, there's the commutator. So this is essentially the Heisenberg equation, and here we have this commutator times C and C dagger times commutator. Okay, it's a little bit unintuitive terms, but this is just coming out from taking these terms here and ordering like this. Okay, so I mean, in general, if you have a completely arbitrary object, then of course the expectation value of, let's say we have a harmonic oscillator, complicated nonlinear harmonic oscillator, then we calculate the expectation value of A dagger. We put it in, and then these terms, if they're complicated jump operators and so on, can give me A dagger squared or A dagger A. So in general, this doesn't help you to solve the problem. Okay, but there are certain cases where it works, and very often, or you can do additional approximations, and without then looking at the density operator, which is often a little bit an object that doesn't tell you a lot, we can directly work with the expectation values. Okay, so this was a bit the general points I want to make, and I don't know, is there any urgent question at this stage? So maybe just to sum up, I mean, this derivation, okay, we went now through all these different steps. I think it's not necessary to remember all of them, but let's say these main ideas with this Markov approximation, then you work out all these commutators, you get these correlation functions of the Barth operators, evaluate them, the Fourier transform at the given system frequency, that's the relevant frequency scale, and this gives you then the rates and also the Hamiltonian corrections. And then whenever we do this, we will end up in an equation like this. Okay, it's the most generic form. And for each dissipation process, it always looks the way 2C rho C dagger minus C dagger C rho minus rho C dagger C. And something that is also natural is if you emit or couple to a zero temperature path, usually you have only this form. But whenever you have a thermal bath, okay, there is also the reverse process. So whenever you can emit photons into a reservoir, then you can also absorb them if the reservoir is in a thermal state. So there will naturally be then always these two components if you couple of thermal reservoirs. And for generic system, of course, that can be much more, okay, can be more complicated. Yeah, then remember, so this is the usual notation that we use. So dot is L rho. It's a linear equation, so that's why the solutions are the exponent of this Liouville operator. And if you want to calculate some expectation values, write it down there. So what is the expectation value? Just write it down in terms of trace, take the derivative, put it in the master equation, and then rearrange the different terms. Yeah, okay, so this is everything quite general. So let's now go back and see and apply this now for a specific system. So our standard case is now the two-level system and coupled to a path of 3D continuum of electromagnetic modes. Okay, so in this case, compared to the Wigner-Weisskopf theory, now we have also a driven system, so there can be some driving fields, and yeah, we have the coupling to the vacuum modes. So what is now our system Hamiltonian? Omega Hg, the excited state, and in rotating wave approximation, we have the driving term, so the laser frequency is coupling the ground and excited state. And again, what we always assume is that, for example, this laser frequency here is close to this transition frequency, so there might be a small detuning, but otherwise, both frequencies are high, but almost the same. The Barth Hamiltonian in this case is our 3D electromagnetic mode. So we sum over all the K vectors and the polarization vectors. And the interaction Hamiltonian is also something that we had before. It's written, I don't know, do I write this GK? Well, I don't write this out explicitly, but you go back to Wigner-Weisskopf theory. These are square root of h bar omega over mode volume. And polarization vector and all these things. Okay, so this here is the same Hamiltonian as for the Wigner-Weisskopf theory. And you see we can write it in this form. And then we can identify the system operator. Here would be a sigma minus. And the B operator would be just a sum over GK AK. Yeah.
Where does the exponential rotation come from for the system, the sigma plus and minus?
Yeah, so this is if you go back to the very first lectures, okay, so we had here a sigma x times cosine
Okay.
omega L times t, and then we did the rotating wave approximation. I mean, we first moved into rotating frame and so on, but it's essentially you do the rotating wave approximation already here.
Thanks.
Yeah, so that was.
So this term is from a classical field driving the
Yeah.
system, and there's also coupling to quantum fields.
Yeah. Yeah. So at this stage we have sure. There's also so we assumed not sure if we do this at some stage a little bit closer, but yeah. So we have now in principle, okay, to be more precise, one of these modes. So we have all the modes, and one of these modes that correspond to the laser frequency is in a classical state. Okay, you can think about this as being in a coherent state, but you can absorb it. So maybe this is coming back to this assumption that the B mode, the average of the B mode is 0. So this is what we assumed. But I also told you, okay, if this is not 0, we can absorb it in the system Hamiltonian. And in this case, this B, because one of the modes is in a coherent state, so it's a finite coherent state, classical field has a finite expectation value. So one of the mode has a finite value, but this value is just a classical number. So therefore we can put it here and the Rabi frequency. But maybe the simplest thing is at this stage, okay, there is some forms, so it's just standard Hamiltonian, and then we add a 3D vacuum field on top of it. Yeah.
For the system Hamiltonian, you have right right hand side you have rotating wave approximation, but on the left term is omega EG should we think it as a Hamiltonian or
So at this stage, so here is everything in the original frame. You can, yeah. So if you now would go to, do the transformation in rotating frame and subtract the laser frequency here, then sigma plus would, so in this transformation, sigma plus would rotate with plus I omega LT. So this would cancel out, this would cancel out. So it could, I mean, we could keep the other terms and afterwards verify that this is the correct way. It's just that, yeah, we already know what we expect. So this is the rotating wave approximation already applied, but in the original lab field. Yeah, but from this, okay, so this is our model that we write down, and then we know, okay, so this is the induction Hamiltonian is really of that form, and we know this jump operator is now sigma minus, and the path operator is this sum, okay, this GK times the AK. Okay, so to now calculate, okay, so first of all, okay, we have now a model, and now we can immediately write down our master equation. Okay, we know the jump operator is sigma minus, so let's plug it in. Then we have these two, sigma minus rho sigma plus, minus sigma plus sigma minus rho sigma plus sigma minus. Okay, and what is this rate gamma here? That's the real, 2 times the real part of our correlation function of this P operator. We also see, you know, we don't have, so usually electromagnetic field is in vacuum, so the other term does not appear, the opposite. We only have, we create an excitation and then we destroy it later. Okay, the other term doesn't exist here because we're in a vacuum, and this is now my gamma rate. And if you now, okay, go back and plug in, okay, this B, that's now my this expression. So I get now twice the sum over k prime. I convert everything, the sum over k's, I convert into integrals over k's, I convert them into integrals over frequency, and you find that this is just the expression that we get from up here, and then convert the k sum into integrals, and this gives you, you know, this density of states, the g of omega squared times this kind of delta function. And you actually find, you know, this gives me pi times with the correct normalization, pi times delta function, and everything else reduces exactly to this form, 2 pi coupling at the atomic frequency times rho, density of states at the atomic frequency, and you just realize this is exactly the same rate as you got from the Wigner-Weisskopf theory. Okay, so this, of course, they are consistent. So the same formalism, but now instead of working out explicitly the wave function of the emitted photon, but we express everything in terms of this correlator. But this correlator, you know, it has this coupling squared, and then you sum it up over all frequencies, and then you do go from sums to integrals, we get the same type of gamma. Yeah.
Where, like, is that an assumption that our bath is in the vacuum state? Like, where does that come in?
So at this stage, I've assumed it, okay, in the sense that we are working now with, think about an atom at optical frequencies, then this N thermal is just 0. Yeah. So you can, you can now immediately work out, okay, so what happens if this in a thermal state, then this correlation function here, so this gives me this expectation value. So here I have the AK dagger expectation value that I plugged in here. And then in general, this would be now N thermal of omega k plus 1. So if you are in a thermal bath, then you would actually amplify, not only have gamma, but N thermal plus 1 is gamma. And there would be also these other components. I think I'll also briefly have it in a later slide. Huh? But at this stage, okay, the simplest case, atom emitting into a vacuum. Okay, so you have this combination. And the thing is, yeah, so if you evaluate these correlation functions, they might look now a little bit different than what you had before, but in principle, they are also more general. So you can now put arbitrary, also other different path operators there and evaluate these correlation functions. So this is a little bit more general expression, but it reduces. And the thing is, because we use the same type of approximation, the same physics behind everything, so therefore we get exactly the same rate, which of course should be, because otherwise we would have made a mistake in either of these approaches. Yeah, okay, so actually it was on the next slide already. So what happens in the, yeah, when I go now to final temperature, so we already discussed, I mean, instead, all these correlation functions that we get are multiplied now by n plus 1. And we also have the opposite term, okay? So we now have, we go back to, so this was the only term we got for the zero temperature path. For finite temperature path, also this is finite. And this, you destroy an excitation you created, this will be proportional to the occupation number in thermal equilibrium. Okay, so this will be proportional to n thermal, and this will be n thermal plus 1. But otherwise, the structure in both cases, you have the same G squared, the same density of state, the same coupling constant, so on. So everything else will stay the same. So therefore, you will also end up in this example. Okay, if this is vacuum, then the thermal in the thermal environment, okay, the first term will be multiplied by n plus 1, and the second one, the opposite term, will now be multiplied by n thermal. Okay, so and if we then, I mean, let's forget about the driving field first, then we would simply have the case where now the excited state can decay, and actually will decay faster if there are excitations in the bath. You know, the bath is hot. Actually, the decay will be faster. You know, so it can be stimulated. You have already photons there. Photons kind of tend to stick together. So you have already stimulated emission. I mean, this is all this Einstein A, B, C, D coefficients, or how they called. So this is the stimulated emission. So the atom decays faster, but at the same time, it can also get excited. Okay, and zero temperature means and thermal goes to 0, and then only the regular decay process occurs. So yeah, so maybe one point, okay, coming back to our this discussion. So far, we just translated everything from our general frame, and therefore, there we in the end wrote down the master equation in the original lab frame. Okay, HS would be now this term, but usually we want to work with the delta. Okay, we want to actually change into a rotating frame here, and then you might think about, okay, how does this now affect my master equation? But you see, I mean, this is not completely general, but let's say for this atomic case, or very often, so if you change the rotating frame, okay, the Hamiltonian now goes over the minus a. You just have this detuning, and all the time dependence here is gone. And you can also see that in the master equation, so this change to rotating frame, so sigma minus goes over to e to the minus I omega EG sigma minus. Okay, and in this master equation, what I always have sigma minus, sigma plus. Okay, so I transform sigma minus and I transform sigma plus. That has, of course, the opposite frequency dependence. So in all these terms, they cancel out. Okay, so I can go to a rotating frame without affecting any of these dissipation terms.
Dissipation terms are the terms other than the commutative.
Yeah, so so this always mean dissipation terms, and here the Hamiltonian. So I do this, I mean, I sit down, you apply this unitary transformation now, not the vector, but the density operator. So it's always then removes this commutator, but here, because I transform this guy and I transform this guy, and they just add up with the different e to the plus omega EG, so they all cancel out. And therefore, this last equation in the rotating frame and the original frame looks the same. So this equation term. Okay, so I can work now with my usual formalism. Okay, so delta and omega, and add now these dissipation terms. One thing, okay, so now to briefly illustrate how do you now do calculations with this term. Okay, so let's go back actually to our formula for expectation values, and for now look at the evolution of, I think, just the general thing. So this is the general equation, and what we had, in our master equation, we had two channels, one with jump operator sigma minus, one with jump operator sigma plus. And in one case, we had this rate, gamma and thermal plus 1. In the other case, we had gamma and thermal. Okay, so in this general framework, we have these two sets of jump operators and the two set of rates. And so then we need, what we want to evaluate now is the occupation, the population imbalance, sigma c. You see, you get some, what you need to do, accommodators, sigma minus sigma c. That's just 2 times sigma minus. The other one is minus 2 sigma plus. Okay, so these are the accommodators that appear here. And if you then plug everything in, okay, so here we have no dynamics, omega is 0, delta is 0, so this term is gone. And from these two terms, we can contribute. So you see what happens here is, for example, this first term, C dagger. So let's evaluate C dagger O C. I first plug in that my C operator is the sigma minus. Okay, then what I have here is a sigma plus, because I take a dagger. I have the sigma C operator, and then I multiply it by sigma minus. This guy gives me something proportional minus 2 sigma plus. Sigma plus, sigma minus times sigma minus would give me something like minus 2 excited state project. Okay, so this is how you evaluate now these expectation values, and then you sum everything together and you get nice simple equation again. And this simply tells you, okay, the time derivative of the population imbalance, you make, for example, excite the atom, or you also prepare it in ground state. This population balance relaxes, it's damped with this rate gamma that is proportional 2 times and thermal plus 1. And okay, get this offset, and this might not be very intuitive, but let's go to the steady state. Okay, look at the long time dynamics where this doesn't change anymore. So sigma dot is 0, and then I can immediately get the population inversion. So expectation value of sigma z at long times. This is then simply 1 over 2n plus 1. And also this expression point. So you have 1 over 2 and thermal plus 1. Now keep in mind that this in thermals is what we get, 1 over 2 times e to the, that's this exponential, okay, h bar omega over kVt minus 1 plus 1 And if I go further, okay, multiply this e to this exponential. Yeah, so this I put here. Okay, this -1, yes, this was missing. And here, so I multiply everything by this exponential -1, I'll bring it up here. And then what I have here is 2, this exponential, and then -1 plus 1, so I get e to the I plus 1. And this I can write e to the I divided by 2. And so everything divided by 2. And if you do this, then you end up no, it's not. So it's essentially then the hyperbolic tangent of 8 bar omega over 2 kBt. Okay, so with this minus sign, so you might remember this this formula. So this is if you go to statistical physics, look at spin systems, non-interacting spin systems, paramagnetism, and you look at the polarization, the magnetization, it has this hyperbolic tangent with this frequency difference. So here you usually have then the magnetic field in there if you have spin systems, frequency difference over 2 kBt. So meaning that this indeed, this equation gives me the correct thermal equilibrium expectation value of the system. Okay, so again, it's a sanity check that we don't doing anything significantly wrong.
Can you just quickly say again why the commutator of H and O doesn't contribute?
Okay, so because here, okay, so here I'm talking about an undriven system.
Right.
Yeah. Then even if you put in a delta, so I mean delta has no meaning, but even if you put in delta, it would commute. Yeah. Okay, so this would be kind of a simple way to calculate expectation values, and then you get the correct equilibrium expectation value. Okay, so it's really by keeping track that we have kind of the correct commutation or expectation value for my path operators. So the path is in the thermal equilibrium, and if I evaluate everything correctly, then also the system coupled to the path will reach a thermal equilibrium. Yeah. Okay, so in this we can then, but this we do tomorrow, we can then also extend to driven systems, and then we do the same type of calculation, then to derive the optical Bloch equations, which we put in by hand in the very beginning. Yeah, but we can do this tomorrow.